Today we're going to be talking about finding maxima and minima in functions of more than one variable. And what we're going to be doing is we're going to be generalizing what you might remember as the second derivative test for concavity from brief calculus. We're going to be generalizing that so we can use it on functions of more than one variable. But before we do that, because we kind of we ran out of time a little bit last time, I want to start with going over how to take higher derivatives of functions of more than one variable. So let's start with this. I'm going to be sharing my screen with you, so let me do that. Okay, and I'm going to start out with this, which is, again, it's a function of two variables. And what I would like you to do to get started is to you try this question. So in order to answer, find all second partial derivatives, you need to find the first partial derivatives with respect to x and y, and then differentiate those again with respect to both variables, okay? So everybody understand what to do? Okay, so then you try this one. Try this, kind of work on it with you, and then we'll come together, okay? But you give this one a try. Actually copy the function down and try to find the partial derivatives. Again, if you have questions, just type them in the chat. I have the chat open so I can see what your questions are. Okay, how's everybody doing with this? Anybody got questions? Okay, if you take a look at what I have on the screen, you can kind of check if you're headed in the right direction. It would be awesome if we could all share our screens together. That would be great. So I could see how you're doing. Okay, let's take a quick look at this, okay? I know you're probably still working, okay? But just to review, when you take a partial derivative of a function of multiple variables, you treat all of the other variables, other than the one you're differentiating, as constants, okay? So if I look at f of xy, and I want the partial derivative with respect to x, the only terms that will give me anything are terms that contain an x. So these three terms will give me something in the partial derivative with respect to x. Okay, the first term is just x's, so I differentiate it normally and I get 2x. This term has constants in it. 3 is a constant, and I'm holding y as a constant when I differentiate x, so y is also a constant. Since the term itself is nothing but constants, it doesn't give me anything in the partial derivative. This term, negative 2xy, since I'm differentiating with respect to x, I'm treating the x like the only variable. And the negative 2y will be a coefficient because, again, negative 2 is a constant because it's a number, and y is being held constant when I'm taking the partial derivative with respect to x. So again, when I differentiate x to the first, I get x to the 0, which is 1. And so that term gives me the negative 2y. The last term is negative 8x. It only has x's in it, so I differentiate it normally, and it gives me negative 8. Okay. Anybody have a problem with the partial derivative with respect to x? Okay. All right. So anybody problems? I'm getting a no. Anybody else? Okay. I'm going to keep going down this column because it's easier to proceed that way rather than flipping over to y. I find the thing most students struggle with partial derivatives is changing their perspective between the two variables. So let's just continue with this one. The notation f sub xx is saying I want the second partial derivative with respect to x, given that the first one was with respect to x. See, that's the 1x. Now I'm differentiating this first derivative with respect to x again with respect to x. There's only one term with an x in it, and that's the first one. So when I differentiate it, I get a 2. Okay? If I wanted to evaluate this at any given value of x and y, you can see it's a constant. There's nowhere to plug in an x and a y. So the value of this is 2, no matter what x and y are. Okay? So essentially, that's just something to understand. If I differentiate this partial derivative with respect to x with respect to y the second time, see the notation, first derivative with respect to x, second one with respect to y. I look at this first derivative, and the only term that's going to give me anything is the one with the y in it. So it gives me negative 2. Okay. Any problem with the second partials? With second partial derivatives? Again, do me a favor and shout out to me in the chat because I can't tell otherwise if you're struggling with anything. Okay, just give me a yes or a no. If we have a yes, we can ask questions. How are we doing? Are you getting the concept of second derivatives? We're just differentiating again. Right. The same concept is working over here when I take the first partial derivative with respect to y. The only difference is I'm changing the variable I'm considering as the variable and what variable I'm considering as constant. When I do this, I'm holding x as constant. So the only terms that give me anything in the first derivative are these two terms with y's in them. X is a constant, so x squared is just a constant. It doesn't give me anything in the derivative. And this term also just has x's in it, so it's a constant. It doesn't give me anything in the derivative. I differentiate 3y squared normally to get 6y. And then in this term, the negative 2x is a constant, and the y is the variable I'm differentiating. So y to the first becomes y to the 0 or 1. And I just keep the constant that's the coefficient, negative 2x. If I continue down in this column and I differentiate my first partial derivative with respect to y again with respect to y, I'm just going to get the 6 from this term right here, because negative 2x is a constant. If I take this first partial derivative and differentiate it again with respect to x, I'm just getting something from the term with the x in it. I get the negative 2. Okay? So again, it requires that you be able to shift your focus between x and y as far as which one's the variable that you're working on and which one's being held constant. And like I said last time, these mixed partials, f sub xy and f sub yx, if you have a continuous function in x and y, no holes or jumps or skips, these two will be the same. Okay? So again, before we move on, any questions on the process? We're going to need to use this for what we're doing today. So please just give me a shout out, yes or no. Yes, I have questions, or no, I'm good. Okay, please just shout out. Again, I've got 4 of you on, so shout out. Questions? Guys, I kind of need you to type something in the chat so I know whether it's okay to go on. Okay, either yes or no. How are we doing? Questions? Okay, good. The rest of you? Awesome. Okay. Then what I'm going to do, like I usually do, I'm going to use a bunch of different materials to kind of share this. I have my notes, which are going to guide us through the discussion. I also have a PowerPoint open because it's much better at perspective drawing these three-dimensional surfaces than I am. And then I have my TI because we're going to try to use that where we can to make life a little easier. Okay, so I'm going to start with my notes. Okay, this is section 17.3. And again, the point here is to try to find the high and the low values of our function, okay, of more than one variable. So for example, if you have a joint cost function, you might want to know what values of the two variables, maybe there are two products that you make and the costs are intertwined, what values of making each of those products minimizes your cost, and what is that minimum cost, okay? So it's the same kind of question that you asked back in brief calculus of functions of one variable. It's just now you've got more than one input for the functions. That's the only difference. Otherwise, we're doing exactly the same thing that we did in brief calculus. Now, you might remember there were 2 ways to do this. You could use the first derivative test, and you could decide, well, is my first derivative positive to the left of me and negative to the right of me? That means the function's increasing up to where I am and then decreasing away, which meant I had a maximum. That was kind of tedious because you had to check multiple intervals. You might remember there was something called a second derivative test for concavity. And what that did, once you found your critical numbers, you could actually just plug them into the second derivative, and you wound up with a real easy test. If your second derivative was negative, your function was concave down, which meant you had a maximum. If your second derivative was positive, your function was concave up, which meant that you had a minimum. Okay, does everybody kind of remember the second derivative test? So what I'm asking is not can you recreate it and actually do it. I'm asking, do you remember hearing about it in Math 213? Remember the second derivative test for concavity. Okay, that's good. Okay, so then it's not totally strange what we're going to do. What you have to realize is with a function of more than one variable, you're extending the idea to handle the two variables. So you might remember the first thing you had to do when you were trying to find a maximum or a minimum in a function of just x was you had to set the derivative equal to 0 and find critical numbers. Remember that? Now, with a function of two variables, you've got to do the same thing, except you've got two first derivatives, one with respect to x and one with respect to y. So let's take a look at relative maxima and minima. Okay. So again, I want you to get the image of this picture that again, it generalizes to a function of two variables. And beyond that, there's really no picture you can have in your mind. But the one for two variables is pretty compelling. Again, imagine you've got a floor, like the floor in our classroom, and imagine that's the XY plane. Okay. So you've got ordered pairs all along the XY plane, all along that surface. And above your head, up floating above us, is the Z surface, okay, that each one of those XY values maps to. Okay. Now, some of those Z points up there are going to be mountaintops, in other words, maxima. Some of them are going to be valleys, so they're going to be minima. And some of them are going to be neither. We'll talk about what those are. Okay, so let one of those ordered pairs on the floor be AB, okay, and let it be the center of a circular region contained in the XY plane, that's the floor. Then if we have a function of XY, okay, for every point in that region on the floor, f of AB, now f of AB is a point Z up on the surface, is a relative or local maximum as long as that Z value is bigger than everything in the neighborhood. That's what this inequality says. If you're up here on the Z surface, which is f of xy, right, the point AB that maps to that Z surface gives you a point that's bigger than anything around it. That's like saying it's a mountaintop. Okay. Same thing for a minimum. Okay. If you've got this point AB on the floor and it maps to a point on the surface that's lower, smaller in value than everything around it, well, that's a relative minimum, okay? So this is just a math-ese way of saying that a point on the XY plane maps to a local maximum up there as long as every point up there around that local maximum is smaller. That's the definition of a mountaintop. Same thing for a valley, that AB maps to a local minimum up there as long as every point around the minimum is bigger than it. That's the definition of a valley, okay? So again, everybody okay with the definition? Okay with the definition? Good. All right. So again, that's a pretty straightforward extension, okay? We've just extended it from a point on a plane to an ordered pair on a plane, okay? Now here's where my drawing falls short, okay? Here's a sketch, okay? And this is meant to be like an upside down basket, okay? And what you want to notice, again, what I'm trying to show you here, is here's the point AB on the floor, and here's the point up here on the surface. You want to notice the tangent line in the x direction, which is f sub x of xy, and the tangent line in the y direction, which is f sub y of xy, when they evaluate at the point AB, these tangent lines are both horizontal, which means the slope is 0, okay? So again, it's not enough to just have one derivative be 0. Do you see how they both have to be 0? Okay, so both tangent lines have to be 0. Okay, so does picture make sense? Picture makes sense with the vertical tangent line, the horizontal tangent lines at the top. And the same thing would be true at a minimum. Okay, let me show you some better drawings with better tangent lines. Okay, I'm going to open up the PowerPoint just briefly to show you pictures. Okay, here's their pretty drawing of a surface where here's AB on the floor, and it's mapping up to the Z value up here. That's a local maximum. It's a high spot. Here's the same idea with a local minimum. They're showing you that circular region around the AB point, where everything up here on the surface, you can see, is a higher Z value than the minimum, right? And here's their better picture of showing you the horizontal tangents. But it's not enough to just take the derivative with respect to x. They both have to be horizontal. Okay, so everybody okay with that? Before we move on, okay, the maximums and the minimums are really clear. Okay, you can get a good picture of that. I want to show you something else that can happen on a three-dimensional surface. And there's nothing that corresponds to this when we have a function of one variable. It's called a saddle surface. So this will be helpful for any of you who ride a horse. Okay, this looks like a saddle. You can imagine in the Y direction would be where you put your legs over the saddle, okay? And in the X direction, here's the front of the saddle, here's the back of the saddle on the horse, right? Okay, this is the equation that gives rise to this surface. And what you want to kind of realize is this point right here is neither a maximum nor a minimum. Or you can think of it as being both at the same time. If you look at it in the X direction, okay, from front to back on the saddle, this point's a low spot. Okay, it's where your butt would be sitting in the saddle. Okay, and then if you look in the Y direction, okay, since your legs hang over the side there, your butt's actually in a high point on the saddle in the Y direction. So you can think of the saddle surface, your book says this point in the middle is neither a maximum or a minimum, or you could think of it as being both at the same time. Okay, so I just want to make sure before we move on, everybody okay with the saddle surface? Okay, as neither being a maximum or a minimum. Okay with that. Again, there is no way I can draw this. Okay, so I want to make sure I show it to you in a graphic. So we have to be able to tell if we have a saddle surface or if we have a maximum like this one. Okay, or if we have a minimum like this one. So we have kind of three cases, and we'll get to those, okay, as we move on. Okay, so back to my notes. The strategy we're going to use for finding potential extrema, okay, is we have to first set our both first derivatives to 0 and come up with the xy pairs on the floor that are critical points, okay? But just because they are critical points, just like with functions of one variable, it doesn't guarantee that they're a maximum or a minimum. You might remember we ran into that situation with functions of one variable. We might wind up with a saddle point, okay? So it's a maximum from one direction and a minimum from the other. So we'll have to check that. Okay, so again, I said plot this in Wolfram alpha, but I just showed you a picture of it. Okay, it's called a hyperbolic paraboloid. You can think of it as a saddle. Okay, so let's show how we do this. I want to find all the critical points for this function of two variables, right? So my strategy is going to be to take both first partial derivatives and set them to 0, okay, and solve for x and y. Remember, this is going to give you a system, okay? Now, we're lucky if you look at this function, okay, it's the highest degree in this function is 2. So when you differentiate it, you're going to wind up with a linear system, okay, which is nice, okay? Linear systems, in most cases, I can solve with a matrix, an RF. If this is higher than a 2, though, you're going to wind up having to solve a nonlinear system, which either is going to take some algebra or it's going to take some sort of online tool to solve the system, okay? So we'll look at both of those so you can get a hang of how to do that, all right? So the first thing I'm going to do is find my first derivatives, first with respect to x, and I'm going to look at it and decide the first term gives me something, the third term gives me something, the fourth term gives me something. Everything else is a constant. Only y's, only numbers. Okay, so differentiating, I get 12x. This is going to give me 6y, because the x, when it differentiates, will give me a 1, and 6y is the coefficient that's left. And here I just get the 36. All right, so here's the derivative with respect to x. If I do the same thing with respect to y, okay, the only terms that give me things are the second and third terms. They're the only ones with a y. So I get 12y. And here, when I differentiate with respect to y, the y will give me y to the 0, which is 1, and the 6x is left behind as a coefficient, okay? So if any time when I'm doing either the calculus part or the algebra part, if you have questions, just please type something in the chat to say, hold on a minute, or I have a question, or something like that, okay? Don't be afraid to stop the train, okay? Now, I have these two partial derivatives, so I'm going to set them to 0. So notice the left-hand side becomes a 0. And you'll see I have two equations that are linear and two unknowns, okay? So I'm going to put them both in standard form. You might remember what that means. That means the x's and y's are on one side in the same order, and the right-hand side has your constant. So the only thing I'm going to do before I actually can put these in my matrix in my calculator is I'm going to subtract 36 from both sides over here to get 36 on the other side of the equation from x and y. Okay, so here are my two equations. 12x plus 6y is negative 36. 6x plus 2y. Again, I just switched the order of terms here. So I have x's for the first column, y's for the second column, constants for the third column, okay? Everybody remember augmented matrices. This is the order you have to put your stuff in order to enter them in. So I'm going to head over to my TI-84, and if you have yours handy, head over there with me. And I'm going to put this set of equations in. You might want to write these down so you have them. Okay, the two equations. And then we'll put them into our matrix. Okay, everybody got it? So going over to TI, I'm going to go to second matrix. And then remember it's edit. And here's matrix A. Okay, again, you might have to clear your matrices or type over them. My matrix had 2 rows and 3 columns, so it's a 2 by 3. Okay, that looks like the right shape. And then I'm going to put the values in. So I had a 12, a 6, and a negative 36 for the first equation. And my second equation was 6 for x, 2 for y, and 0 for the right-hand side. Okay, so that's how I translate that system. I'm just taking the coefficients and the constants, and I'm putting them in the matrix. That's why it's important that everything be in the same order, because the matrix is keeping track of first column's x, second column's y, third column is the right side. Okay. Once I get that in there, I'm going to use RF So again, that's in my matrix math menu. And you might remember it's faster to go backwards to B. So I take RF and then I put matrix A in there. Okay. And if I take a look at this, what am I getting as my values? Okay, so I'm asking you a question. What values did I get? Okay, so X, you might remember the way you read this, 1X plus no Y's is 6. No X's plus 1Y is negative 18. So yes, Joanne, it is X is 6 and Y is negative 18. Okay, so again, please don't crank the algebra by hand if your system's linear. Just put it in standard form, use RF. Okay. Let's go back here to the notes. Okay, and again, I'm showing you what I got. Oh, wait, what happened? Did I copy them wrong? 12 and 6 is negative. I didn't get that value. Let me go back to my matrix. I probably messed up what I typed in. Let's go back to edit. I forgot. Oh, yeah, negative 36. For some odd reason, when I did it the first time, I got negative 4 and 2. I can't imagine what went wrong this time. Okay, let's try it again. I got 6 and negative 18. It did not get negative. Okay, can't figure out what went wrong here. Okay, I'm trying to figure out why. I must have missed a sign somehow. Figure out why else this would be wrong. Oh, I know what I did. I made a typo back in my notes. Okay, take a look. Okay, back up. My bad. Okay, when I rewrote my notes, I lost a 1. Let me show you right here. Okay, so this should be a 12. So let me put a comment over here at sticky note. Over here should be 12y plus 6x equals 0. Okay, two equations are, okay, so it's 6x plus 12y equals 0. And the other equation's correct, 12x plus 6y equals negative 36. Everybody understand where I screwed up? It's the same. Okay. No, I made a typo here. When I copied this equation, I copied just a 2 instead of a 12. Don't worry, I'll fix the notes. Okay. That's why when I went and I put it in the calculator, okay, I wasn't looking at this equation. I was looking at something else. Okay, I was actually going back to the originals. Let's try the correct 2 equations. Okay, so basically the one that has a 0 on the right side should have a 12 for y instead of a 2. So let me go back there. Go back into my matrix, edit it. Okay, so this one, this 2 here should actually be a 12. So let me go over there and change that and make it. Okay. So you didn't realize. Yeah, I know. Well, it's great when everybody makes mistakes. What's important is how to go about finding them. Okay. So the first thing I did when I realized I wasn't matching my notes was, and again, I graphed this thing so I knew where the critical number should be. I went back and I looked for typos. That's almost always the first thing. First, I looked for typos in the matrix, and then I went back to my notes and looked for typos there. So it's important to know how to debug because everybody makes mistakes. Okay. So let me try this again. So let's quit out of here and try the RREF again. Second. And there's our -4.2. Okay. So our values, okay, we get x equals -4 and y is 2. Yeah. Okay. So everybody understand my mistake. Okay. I want you to make sure you're not getting confused because I made a typo. Everybody understand what I did? Okay. And I'll fix the notes, don't worry, so they make sense. Anybody got any questions at this point? Everybody all right with this? All right, let's go back to the notes. Okay, and again, I'll push this sticky note away. So I got -4 and 2. That means if this surface has a maximum or a minimum, it's above the point -4.2 on the floor. There's maybe a valley, or there's a mountaintop, or there's a saddle surface above that point. That's what it means. Okay, so at this point, we just know we have something, but we don't know if it's a maximum, a minimum, or a saddle point. So here's the test that's the extension of the second derivative test for extrema. Okay, it's called test for relative extrema. So we're saying, let's let all the second partial derivatives of f exist in this region around your critical point that you already found by setting your first derivatives to 0. Okay, we're going to define, well, again, here's our first derivatives equaling to 0. Okay, that's the part we already did. Okay. We're building this value d called the discriminant. And what it is, it's the second partial derivative with respect to x evaluated at the critical point you found, times the second partial derivative with respect to y evaluated at the critical point you found, minus the mixed partial. It doesn't matter which one you pick, right? Because these are going to be equal if you've got a continuous function, evaluated at that same critical number squared. Okay, this discriminant will tell you whether you have an extremum, like a valley or a mountaintop, or whether it's a saddle. Okay, now if the discriminant's positive, okay, so if it's positive, that means you have a maximum or a minimum. Okay, so if this value comes out to be greater than 0, you have a maximum or a minimum. Which is it? Okay, if your first partial with respect to x is negative, okay, you might remember the second derivative test. Negative second derivative, you've got a maximum. Okay, you're concave down, right? So if your discriminant is positive and this second derivative with respect to x is positive, right? Second derivative positive, you've got a minimum. Okay, so this is the test right here. If the discriminant is negative, it's not positive, then that means you didn't get a maximum or a minimum, you got a saddle. Got a saddle point. And if d is 0, the test fails. It doesn't tell you anything. You need to use different methods to find a maximum or a minimum. Okay, don't worry. In most of the examples you're doing, you're going to get D either equal being a positive value, so you'll have a maximum or a minimum, or you're going to get it being negative. Now, it's possible if you've got a complicated enough function to start with, you can have a relative maximum here, a relative minimum here, and a saddle somewhere else, right? It's a surface. It's like a landscape. So there could be a lot going on, okay? Does this sort of make sense? This D value is controlling whether you have maximum or minimum or whether it's a saddle, okay? So either one, okay? Because notice in both these cases, D is positive, and you're using this second derivative with respect to X to tell you whether it's concave down or concave up, right? Here's a clearer way to look at it like a table, okay? So if D is greater than 0, okay, and F, the second derivative with respect to X is negative, you've got a relative max, okay? D is greater than 0, you've got the second derivative positive, you've got a relative min. D is equal to 0, it doesn't matter about the second derivative, you have got no information. And if D is negative, you've got a saddle point. Okay? Is this clear? Okay, is the test clear? I'm not saying you could use it yourself yet without going through an example, but does this kind of make sense? You've got two things going on. First, this discriminant value, and then the second derivative with respect to X, okay? So it's like a two-level test. First you test D, then you test the second derivative. Okay, let's take a look. In that previous example, the only critical point we got for our function was -4, 2. Let's figure out what it is, okay? Does this ordered pair on the floor to a maximum, a minimum, or a saddle point? Or possibly none of these if the discriminant is 0. So the first thing you need to do is find the second order derivatives. So putting the first order derivatives here again, because it's a lot easier. I wrote it right this time, you can see, okay? When I take the second derivative, I want to make sure I have all this in one place to build a discriminant, okay? So differentiating this with respect to X a second time gives me a 12. Differentiating this the second time with respect to Y gives me a 6. Notice there's no place to plug in -4, 2, because these are constants. If your original function started out as a higher degree function, say cubic, there would be a place to plug in the value -4, 2, but I can't plug it into a constant. There's no X and Y here. That makes it easy. That's a good thing. All right, here's my first derivative with respect to Y. If I differentiate this again with respect to Y, I get 12. If I differentiate it with respect to X, I get 6. Now let's build the discriminant. Okay, it's the second derivative with respect to X. Okay, I can't plug this in anywhere. Okay, my second derivative was a constant 12, so I'm just writing the 12. It's important to understand that this is not evaluated at -4, 2 because the second derivative was a constant, right? I started with something to the second power, the first derivative was linear, the second derivative is going to be constant, right? Because you drop the degree each time. Okay, so f sub xx is 12. F sub yy was also 12, and likewise, I could not evaluate that at this critical point. And then the mixed partial was a 6, okay? So here are the numbers going in, xx, yy minus xy squared. This gives me 144 minus 36. So my discriminant is a positive number. Again, I don't care what it is, I'm just testing its sign. Okay? And I'm making my note over here, since our second derivatives are constant, I didn't actually plug in the values. Okay, is everybody okay with the evaluation of the discriminant? Evaluating D, okay? You see where I'm getting the numbers from. Anybody else having any questions? We're good. Okay, well, my discriminant is positive, and you might remember from that table here, positive discriminant means I've got either a maximum or a minimum. I just need to look at f sub xx to decide. F sub xx is a positive 12. So if you again look at the table, okay, f sub xx is a positive number. That means that negative 4, 2 has a relative minimum over it. Okay. So f sub xx is positive. That means f of negative 4, 2 is a relative minimum. What's the value at that minimum point? That's where you go back to your original function, f sub xy, and you plug in the critical point you found by setting the first derivatives equal to 0. Okay? So I'm plugging in negative 4 for x, plugging in 2 for y, and I'm getting negative 77. And I'm saying I can plot the surface with Wolfram alpha just to eyeball it. Okay, so let me go over to Wolfram alpha. See where that is. Close this for a minute. 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 Here's Wolfram alpha. Okay, here was my original function. Okay, 6x squared plus 6y squared plus 6xy plus 36x. This is just wolframalpha.com. And again, the command is plot z equals. Okay. And again, you can see I get this wet sheet looking thing. Here is a cross section of it. And again, the redder the values get, the lower the surface. So you can see I have a low spot here. So I can tell from this graph, I've got a low spot. And you can see, here's my x value. It's slightly to the left of 0. That would be negative 4. And it's slightly above 0 here. So the center of it would probably be at negative 4, too. Again, with the free version of Wolfram alpha, you don't get a lot of functionality. You just get a very gross picture. Okay. So do the second derivative on the TI. The only thing your calculator will do would be to evaluate a second derivative. Okay. So if you remember, you can evaluate a derivative at a point. That might be helpful if you want to break it into pieces. But again, your TI is not terribly helpful for partial derivatives, okay? You'd be better off using something like Symbolab. Okay, Symbolab has partial derivatives in it. Let me see if I can bring that up. I'm trying to make this go away so I can bring it. See if I can bring up a new tab and then make it big. Okay, calculus. See if I can find partial derivatives. Okay, see this? Okay, this is a partial derivative with respect to x. So you would be able to put a function of 2 variables in here, and you would be able to take a partial. Okay, so you'd say d dx, and then you'd put your function of 2 variables in here. Okay, so as far as help with doing that. Confused with the signs. Okay, if you ever are in a situation like that where you're confused with the signs on everything, then please email me with the problem and I can walk you through it. Please email me with a problem. If you're using any kind of technology and you get confused, okay, you can take a screenshot, right? Like down over here. If you're on a PC, you've got something called a snipping tool. Okay, so snipping tool. And once that's open, it's little scissors at the bottom. And I can just click on it. And I can just take a picture of whatever I want to see on the screen like that. Okay. So you can take a snip of your screen and then just paste it into your email or attach it if you want to save it. Okay. but please let me help you if you're struggling. Okay, you can see they have some examples here with functions of two variables and they're taking partial derivatives. Okay, these are just examples. And the benefit of Symbolab is it will actually show you steps. Okay, so if you're looking for technology, not a problem. Okay, anybody have any other questions? All right. Now, again, what I'd like to do before we get into this one is I want you to try one. So I'm going to go back over to our worksheet over here. And let me see if we can do this one. Okay, so I want to put this on a second page, right? So here's our location of extrema. Okay, you're going to set your first derivatives with respect to x equal to 0. Then here's the test. Okay, you're going to build the discriminant, and here's how you decide what you've got. Okay, so here's a function. Determine the critical points. Okay, and again, let's see what I've got over here. I didn't put a function in. Let me do that. Try this one. Have f of x, y equals, and it's going to be x squared plus 3y squared minus 2xy minus 8x. Okay, so you try this one. Okay, everybody understand what I need you to do? I need you to try this one. And again, I'll be working on it over here. How are we doing? Anybody stuck? Okay, if you take a look at what I have on the screen, I've set my first derivatives equal to 0. I've put them in a matrix and are refed because they were linear. And I've got my critical points. Sorry, backwards. That's 6, 2. So x is 6. Was everybody able to get this far at least? Okay. Keep on working, then we have to build a second derivatives. And then the discriminant. Yep. X is 6 and y is 2. That's correct. Right now you've got to figure out, well, does 6, 2 on the floor give you a valley? Does it give you a mountaintop, or does it give you a saddle? So you need to build the discriminant. Before you do that, you need to find the second derivatives. Okay, that's what I'm doing here. Okay, guys, I know you're probably still working, but let's all come together so I'm sure we're all in the same spot, okay? Again, let's just review taking the first partials, okay? Make sure that you got these values, all right? And then once you get these, you set them to 0. Then I put them in standard form. That means x first, then y, then the constant on the other side. So here I added 8 to both sides. Here I just switched the order and I made it negative 2x plus 6y equals 0. Once they're in standard form, you just plug them into a matrix. Here's the first equation. Here's the second one. And use ref to get the value of x and y, okay? In this case, there's only one value, 6, 2. Right? And then I need to figure out whether it's a maximum, a minimum, or neither. So I need to build the discriminant, and it requires second derivatives. So here's my first partial with respect to x, first partial with respect to y. I'm just copying these over because I'm going to use them to take the second derivative with respect to x. That just gives me the positive 2. And then the mixed partial, that's this with respect to y, gives me negative 2. Same thing over here. I take the second partial with respect to y, that gives me 6. Second partial with respect to x, negative 2. Kind of a sanity check is these mixed partials should be the same. Right? Here's the discriminant. I want to evaluate the second partial with respect to x at 6, 2. Again, they're constants. There's no place to plug in 6, 2. That won't always be the case, all right? But I'm putting that here just so you realize that the actual discriminant requires that you plug in the value of the critical point, okay? If it's a constant, you're just stuck with a constant. So here's f sub xx, f sub yy, and then minus the mixed partial squared, okay? So if I square negative 2, I get a positive 4. 2 times 6 is 12. 12 minus 4 is 8. 8's a positive number. Great. That means our critical point is going to give us a maximum or a minimum. I look at the sign on f sub xx to tell that second derivative being positive means I have a concave up function, and that means I have a minimum value. Again, I'm just using this rule up here. Okay. So again, d is a positive number, and f sub xx is positive, so I have a relative minimum. Let me ask, how are you doing with this example? Are you okay with the example? Anybody questions with the example? Okay. Now, if you wanted to find what the minimum value was, okay, the minimum value is basically you start with this function here, your original function, and you're going to plug in the 6, 2. So I have 6 here, x, 2 for y. Right, so again, I have a 6 here. Six, 2. Okay, so this is simply just something you evaluate on your calculator. Okay, I'm going to do that right now. So that's 6 squared. Two times 6 times 2. I got negative 24. So again, if they ask you for the minimum value, you've got to plug this back into your original function. So it's pretty much doing it step by step. Hope it's all like that. Yeah, it's all like that as long as your original function only has squares in it. Let me take you through an example that's a little bit more complicated. Okay. What I'd like to do is I have an extra example in the notes that I'm pretty much going to skip over, and I'm going to go to an applied problem because I just want to make sure we actually get to everything today. So you can take a look at the notes where I walk through a separate problem. Okay, example 3. See this one? Okay, no. Example 3 is going to give you quadratic first derivatives and linear second derivatives. Okay. I can do a problem that's very similar to this. Okay, but it's also an applied problem. Okay, so I'm going to let you do example 3, like read through example 3 on your own. Okay. And I'm going to go through the applied problem because I want to make sure you're comfortable applying this. Okay. So example 3 is where you're going to want to having to crank through the algebra or use some technology to solve a nonlinear system. Okay. Don't worry, I walk through it step by step. Okay. Now, normally, if you've got a higher degree original equation, you're going to wind up with multiple points to test, right? If your first derivatives are quadratic, chances are you're going to get multiple solutions, okay? So one might be a minimum, one might be a maximum, one might be a maximum, one might be a saddle point. You've got to keep track of it all. But it's bookkeeping. It's not hard. It's just tedious, okay? So it's more a chance of just pay attention to what you've got, okay? So here's the application example I want to do. I want you to see what use this is. Okay, so a company is developing a new soft drink. The cost in dollars to produce a batch of the drink, and we're not saying how much a batch is C of XY, where X is the number of kilograms of sugar that go in the batch, and Y are the number of grams of flavoring. Okay, so imagine you're making some sort of soda, okay, a cola or whatever. It's sweet, so it's got lots of sugar in it. And then there's this secret recipe of spices that goes into it. And that's a little bit smaller, right? So X is in kilograms, Y is in grams, okay? So we want to know what are the amounts of sugar and flavoring I have to put in a batch that will help me minimize my cost, okay? So I want to make something I can sell that's according to this formula here, but that is at minimum cost. So if I want to find a minimum or a maximum, I take my first derivatives and I set them to 0. So take a look at this function up here. Okay. If I'm differentiating with respect to x, I'm only going to get something out of these two middle terms, right? So 3 times 27 is 81, drop the exponent on x. Here, okay, the derivative with respect to x is a 1, and negative 72y comes along as the coefficient. If I differentiate with respect to y, okay, I'm only going to get something out of the last two terms, right? This term, okay, if I'm differentiating with respect to y, the y will give me a 1, and I'll get negative 72x as the coefficient. And here I'll get negative 16y. Set these both to 0. Now you can see I don't have two linear functions. This one's linear, but this one's not. Okay, so matrices is gonna work for me. So I have to try to figure out, okay, how do I approach this? I can probably solve this for either one of the variables, or it would probably take this first equation and solve for y in terms of x, right? Because it's easier to solve for y. If I solve for x, I'm going to take a square root, and I'd rather not do that because it gives me two values. So let's solve for y in terms of x. So I'm going to add 72y to both sides first. Okay, so now it's on the other side of the equation and it's positive. I'm going to divide both sides by 72, and I get 81x squared over 72. I can divide a 9 out of both of these numbers, okay, and that gives me 9/8 x squared. Okay, so y is 9/8 x squared. What I can do next is to go over to the second equation, right? And since y is equal to this expression with x in it, I'm going to plug in 9/8 x squared in place of the y. Everybody see that? Okay, so again, what I'm asking you is see the substitution. Okay, see the substitution for y over here. Okay. All right. Now, let's do some simplifying. You can see that 8, I can divide the 8 out of the denominator here, right? 8 goes into 8 once, 8 goes into 16 twice. Then I have 2 times 9 is 18x squared. Yay, I got rid of the fraction, okay? This is an example where algebra is going to help you simplify what you're doing, okay? So I have negative 72x plus 18x squared. It's a quadratic, so let me put it in the order I'm comfortable with the squared term first, minus the linear term. And then I'm looking to see, hey, any common factors? Okay, yeah, I can factor out an 18 and an x, right? Because 18 does go into 72. And again, x goes into x squared and x goes into x. So I'm dividing out 18x from 18x squared. That leaves an x. And negative 72x divided by 18x leaves a negative 4. Okay. Then I'm going to set both of the terms that I have an x in to 0. So 18x is 0. Divide both sides by 18. That gives you x is 0. X minus 4 is 0. Add the 4 to both sides. So here are my two x values, okay, that will lead to critical points. I have two x values that lead to critical points. Okay, everybody good with that? Okay, so now I need to plug each one of these into my equation up here for y to find the y that goes with it. Okay, again, it's natural you'd get more than one critical point because you started with a higher degree equation. Okay, so I go back to the equation that's solved for y. Y is 9/8 x squared, and I'm going to plug both these values in. If I plug in the 0, that's easy. 0 squared is 0, 0 times 9/8 is 0. So 0, 0, the point that's at the origin of my xy plane, is going to give rise to a critical value. Okay, here's the 4, the other x value going in. This is 16. Okay, again, 8 goes into 16 twice. So this gives me a 9 times 2 is 18, right? So here are my two critical values, my two critical points. Okay, understand how I got two critical. Okay, everybody understand where the two critical points came from? Anybody else got a question? Are we good? Okay. Now I've got to test both of these. Okay, so I need to build the discriminant, and then I've got to plug both of these in, okay, and see what they give me, right? So first, let me find my second order partial derivatives, okay? And again, just take my word for it. These are the partial derivatives, okay? Here's the second partial with respect to x, second partial with respect to y, and the mixed partials match. But you can see, because of that higher original value on my x term, I had an x cubed in my original equation. Now, when I'm down to second derivative territory, I've still got an x laying around. So I can plug in at least my x value from these pairs when I evaluate my discriminant. Okay, so let's watch how I do that. Okay, so I'm building the discriminant for both critical values. So here it is for the first critical value, 0, 0. So again, I'm plugging in these. Remember, again, I can only plug it in to where I have an X, okay? So if you take a look, my second partial with respect to X has room for me to plug in the 0. So 162 times 0, CYY is just 16, okay? And the mixed partials are negative 72, okay? So 0, 0, if you evaluate this gives you a 0. 0 times 16 is 0. And this, whatever it is going to be a huge negative number, right? So this first term is a 0, because of this, right? So my discriminant for 0, 0 is negative, a negative number. That means over the origin on the XY plane, I have a saddle point, okay? So this is a saddle point. It's not a maximum or a minimum. Since I was trying to find a minimum cost, I'm going to ignore this value. It's not a minimum, okay? So everybody understand how D gave me a saddle point. Okay, everybody understand why 0, 0 gives rise to a saddle? Yes. Let's try the other one. Maybe we'll get lucky and it'll be a minimum. Okay, that was the point 418. Okay, so look at B down here. I'm plugging in the 4 because my second derivative with respect to X was 162X. None of the other second derivatives have any place to plug in any of the values. They're just constants. So here I have 162 times 4. Here's the FYY, and here's the mixed partial again. So this gives me 10,368 minus 5184, which is 5184. Yay, my D value is a positive number. That means I have a maximum or a minimum. And again, if you look at C sub XX evaluated at my critical value, again, I'm plugging in the 4, it's a positive number, okay? So if I have a f sub xx being positive, that means my function's concave up, and that means I have a relative minimum, okay? Everybody understand how I got the relative minimum? Okay, everybody understand how 418 gives you a 1? Okay, so it's a two-stepper. You first got to check D, then you check C sub xx. Okay. The last thing we were asked was, okay, find what the minimum cost is. So I have to plug that back in the original function. Okay, so I'm putting 418 into the original function. I get 1336. Now here's the critical part. This was an applied problem. So the answer isn't in terms of X or Y or C of XX or any of that stuff. You want to interpret it in English. This is a cost. Okay. The minimum cost per batch is $1,336. And you get that when you use 4 kilograms of sugar, that's your X, and 18 grams of flavoring. Okay. So let me ask, everybody understand the interpretation? Everybody understand the interpretation? Anybody have any questions about the interpretation? Okay, it's just a matter of keeping track of what the variables represent. Okay. Are we good to keep going? Okay, the only thing we have left to do is to have you try one of these. Okay. Right, and that's what I have up here. I said the profit in thousands of dollars that Metropolitan Metalworks earns from producing X tons of steel and Y tons of aluminum can be approximated by this equation. Find the amounts of steel and aluminum that maximize the profit and find the maximum profit. Interpret the answer to the question in an English sentence. That means no X's and Y's. Okay? So you try this one. Try this one. I'll work it down here. Okay, again, if you get stuck or you have questions, just pop something in the chat and I'll answer you, okay? How are we doing? Okay. Okay, y equals 1. I'm stuck. Okay, let's take a look. I want to make sure everybody isn't stuck on algebra. Okay, so please follow me. Okay, I know you're still working on this, but take a look over here where we're taking the first partials with respect to x. Okay, only the first two terms will give me anything. If I differentiate this first term with respect to x, I get 36y. If I differentiate the second term with respect to x, I get negative 3x squared. Okay, if I differentiate this with respect to y, I only get something out of the first and last term. The first term gives me a 36x, and the last term gives me negative 24y squared. Everybody okay with the derivatives and setting them to 0? Okay? So okay with first derivatives. Okay, with the first derivatives. Okay, and then we're setting them to 0 here. And again, remember what you need to do. You need to solve for the variable that's easy to solve. Okay, so I picked this first equation. You could have done it the other way around. It doesn't matter. But I'm going to solve this for y. Okay, so I'm putting the 3x squared on the other side. I'm adding 3x squared to both sides to try to isolate y. Then I'm dividing by 36. Okay, that gives me 3 divided by 36x squared. I can cancel out a 3 from both of these and get 1/12. X squared equals y. Everybody good with that? Okay. Then what I'm going to do is I'm going to plug that into the second equation for y. Okay, so here's 1/12 x squared going in for y, and y is squared here. So remember how you square a product. You square them separately. 1 squared is 1. 12 squared is 144. X squared is x to the 4th. Okay, that's just rules for exponents. Okay, then you might notice here, hey, I got a 144 on the bottom and a 24 up in the numerator. Maybe I can cancel that out. And 24 does divide evenly 6 times into 144. So here's what I've got. Everybody okay with that? Okay, okay with the substitution. Okay, with the substitution and simplifying down here. Okay, the next thing I'm trying to do is to divide out a common factor. So dividing out a 1/6, and I'm dividing out an x. So I'm dividing out 1/6 x. Now, remember, factoring out is a divide operation. So you take 36 and you divide it by 1/6. That gives you 216. Okay, and here I'm dividing negative 1/6 x to the 4th by 1/6 x. The 1/6 cancel and leave a negative 1. And x to the 4th divided by x is x cubed. Are we all right with the factoring? Okay. All right. Now what I need to do is I need to set both my factors to 0. So let's see where I am down here. Search. I want to set 1/6 x is 0. Okay, and this is 0. 216 x minus x cubed is 0. Okay, so here's what I have. Okay, you can see here, if this is 0, I'm going to multiply both sides by 6, and I'm going to get x equals 0. Guess I should say not and, I should say or. 4. And then I have 216 equals x cubed. Okay, so I'm just getting my x cubed on the other side, and it's positive. Okay, and then I'm going to take the cube root on my calculator of x16, 216. That's on your math menu. Okay, it's actually number 4. So you take cube root, put 216 in there, and I get a 6. Okay, remember the cube root is going to have the same sign as the number you're taking the cube root of. So again, I have x equals 0 or x equals 6. Okay, so those are my values. Now I have to go back up and substitute those both values into my y equation. Okay, so substitute both of these into those x values. Okay, so here's what I have. All right, and then let's do the first one. Okay, that's easy. I'm putting in a 0. See if I can. Equals y, so that's easy. Y is 0. Okay, and then if I do this again with the other value, what am I putting in? I'm putting in it's not doing it. Okay, so I'm putting in my 6. Okay, so 6 squared then is 36. Okay, 36 divided by 12 gives me 3. Okay, so I have that. Okay, here's my second equation. I want to say or y equals 0, and here I have y. Okay, so everybody okay with this? Okay, I'm just substituting back. Okay, so my 2 critical points are 0, 0, and 6, 3. Everybody good with that? Anybody questions? Good with critical points? Okay. So now what we want to do is test. Okay, so I have to build my second order derivatives. So I'm going to pull these up here again. The first derivative so I can see them. Okay, so I'm going to build second derivatives. Okay, because I need to be able to plug them into D. Okay, so insert. So P sub XX, okay, of XY. Okay, so if I differentiate again with respect to X, I'm going to get negative 6X. And if I differentiate with respect to Y again, P sub YY. I'm doing this one again. You can see I'm going to get negative 48Y. Okay, everybody all right with those two? Okay, and then let's do the mixed partials. So if I differentiate my first derivative with respect to x with respect to y, okay, that would give me just 36, starting here. And let's do yx over here. Okay, and you can see I would also get 36. Lost an equal sign. All right, everybody all right with the second derivatives? Okay, with the second derivatives? Right, so then I have to build my d. D for each critical point. So let me go here and do 4, 0, my second one would be 4, 6, 3. Just so I can separate them. You can see how a lot of this is organization. Okay, so let me go back up and grab formula for D. I'm just taking one of the formulas that I have on my sheet, and I'll plug in the right values for the ordered pair. Right here, I want to plug in 0, 0. Okay, and then I'm going to actually put in the values here. So insert. Okay, the first derivative here would be minus 6. And again, I can plug in the x value, that's 0. Okay, and then I have f sub y. Okay, and that's going to be negative 48 with y as 0. Okay, so that gives me a 0. And then I have the mixed partial, which is just 36, and it's going to be squared. Okay, negative 36 squared. Yep. Okay, and we basically already figured out that's going to be a negative number, right? Because these first two give you 0 times 0 is 0. So it's 0 minus, and again, 36 squared is 1296. So I get negative 1296. And what does that tell you about the point 0, 0? Anybody want to give it a shot? The point 0, 0 gives rise to a what? Anybody remember what a negative discriminant means? It's a saddle, yes, saddle. So we know that we aren't going to get any minimum out of here, okay, or maximum. I guess we're looking for profit. So let's try the other point. Okay, I'm going to do the same thing here, only I'm going to plug in this ordered pair, okay, which was 6, 3. Three, 6, 3. Okay, and then I have this that I'm going to put down here. Okay, so now I'm putting in the x value in x sub x. Okay, and my x value here is 6. And I'm putting the y value into my f sub y, that's the 3. Okay, so now I get to evaluate this. Okay, so I have negative 6 times 6 times negative 48 times 3, which gives me 5184. Okay, for the first part. We already said negative 36, 36 squared is 1296. So I'm going to subtract that. Okay, and you can see just by looking at it that we're going to wind up with a positive number, which is 3,888. Okay, so since D is positive, that means we get to look at F P sub x evaluated at the critical value. Okay, so look at this evaluated at 6, 3. You can see there's no place to plug in the y value, but I can plug in the 6 for x. That gives me negative 36. Okay, so since the second derivative is negative, right, that means what? That means concave down. So 6, 3 gives rise to a maximum. All right, now they asked us for a maximum value, so let's evaluate it, evaluate our original function. Okay, so got to go way back up here to get my original function. That's my profit function. Okay, and I'm going to put that right here. Okay, and then I'm going to put in 6, 3. Yeah, with a comma. All right, so everywhere I see an X, I'm putting in a 6. Everywhere I see a Y, I'm putting in a 3. Okay. Again, this is a calculator problem, so hopefully you're doing this with me. We're almost there, guys. I know this has been a long session. Yep. Okay, so I got 216. Now the last part was the interpretation. Okay, remember, this was a profit. So I'm going to say profit is maximized at $216. Okay, per, what was I doing here? 216, is it in thousands? What was it in? Yeah, thousands, $216,000 when, and again, these were tons of things, weren't they? X tons of steel and Y tons of aluminum. Okay, so when 6 tons of steel and 3 tons of aluminum are manufactured. Steel. Okay, is everybody all right with the interpretation? Yes, exactly. Okay. And again, this is, it's a lot of steps. Again, what makes it long are the algebraic steps in the middle. If you're having difficulty with those and you're looking for a way to quickly solve a system that's not linear, I'd suggest poking around in Symbol Lab. If you still want some guidance on how to do that, that doesn't require you to crank through all the algebra, although you should be able to do it, just email me separately, okay? Like, especially if you're doing a homework problem in this section and you get stuck on one of these, please email me and I'll be happy to work it through with you, okay? So I'm going to stop sharing and I'm going to ask if we've got any questions at all. Any other questions? Anybody, any other questions? We good? Okay, thank you for sticking with me. I know it was a long session, but it's a good thing that you did this because it's going to be important going forward. Okay. Are we good? I'm going to stop recording.